Hello, hello. I don't know if you can hear. Good morning, Luna. Thank you. And I guess that means you can hear me. I hope, I think. Good morning, Luna. Thank you. Um, good morning, David. Thank you. Good morning, Molly. Good morning, Catherine. Thank you, Luna. Appreciate that. Okay, awesome. Making sure. Thank you, Luna. Good morning, Michelle. Hello, and good morning, Amarani. No, I think. You're going to correct me. I'm getting there. I know. Amarani, I'm saying, I think. Tell me again. All right. Good morning, Darina. Good morning, Ashley. Yeah, good. Phew. Thank you. Okay. The only problem is I can't pronounce yes. Yes. No, I can't. Okay. Good morning, Daniel. Thank you. And Daniel is a name that I do know how to pronounce for some strange reason, although I have problems with O. Good morning. Yes. Okay. Oh, more people. Sorry. Okay. And all right. So many. I'm going to just like dive in even as people are coming in. Here's the because I know, okay, so it's like exam time. We could have feelings, stuff like that. Also, I'm a little bit ragged, as you met. Like my son is homeschooled, so things are a little bit. And actually, to be honest, I'm canceling my other classes, but we're doing this one because I know we're concerned about the exam, and there's a lot of stuff I want to get to you. Um, but please forgive if I go a little bit something. I will tell you right now. In fact, I'll try to be more clear. This may not be the most interesting class ever or something like that, but I will tell you regarding grades, I think this will be the most important class we've had thus far. Like, I think you'll get the most information that's most directly related to maximizing your grade. Good morning, Nikaya. Thank you. Good morning. What I'm really trying to say really quickly now is like, I'm going to go a little fast. I'm going to say a lot of things today, but anything I say about physics, you'll have time to think about and sink in and practice and stuff. But I'm going to say a lot of things about this exam. I mean, that's all we're talking about today is the exam. I promise. That's all we're talking about. And everything I say today is meant to maximize your grade and minimize anxiety when possible. Like it's not about a trick. Remember, I want you to get an A. Also, it's important to remember that. Like in that, so don't look for trick. Assume that whenever in doubt, we're on the same side as best as we can be. What I'm really trying to get at here is to be a super. Sorry. And good morning, Melissa. Thank you. What I'm really trying to get at here is I'm going to try to answer any concern that I might have, that you might have about this exam. And I know the solutions, and hopefully you just got the rest of the solutions in your box, hopefully, and please take them out or whatever. We're going to talk about them. I'm going to try to, what I'm trying to say is if there were ever a video that you would ever want to have access to and watch and use, it's going to be the video from this class. Like, let me be even more like clear about that. Okay. And good morning, Alyssa. You haven't missed anything yet. We're going to start talking about the solutions today, but I'm going to say a lot of really concrete things like, okay, this part here will not be on your exam, or I'm going to say like right here, I am going to change this number or something, like little things that I'm not going to write into Google Classroom. I'm going to say them today. And it'll be recorded and it'll be posted on YouTube and all that. And if you have any friend who's not in class today, please like inform them. Or, if you have to space out or leave today, just please know that I'm going to say a lot of really specific things about the exam that will be on the video too. So they're meant for you to know, but I can't write them a million times. I'm only going to be able to say them. So actually, to be even more clear before I begin, I may have said this before, but let me be as super clear as possible. And I'm not trying to make anybody nervous. I'm a little nervous because I want to get to everything before the period ends. And I know you just got the remainder of the solutions in your box like 10 minutes ago, and I'm aware of that. We're going to address that. But one thing, and this seems to work in the other classes, I'm typing in the chat right now. Oh yeah, no, I think I've told you this because some of you are using this and you're using it very well. Remember, that's my cell number. The deal with the cell is, especially during an exam, you are allowed to text me with questions. You are. And I do, in a situation like this, I do prefer texting to email or to Google Classroom. Like if you want a fast answer to something, like text me, but you have to identify who you are. Like say, like this is Ashley from 203 or whatever, from your 203 class or whatever. And you have to ask me a question that I can answer concretely and quickly, like a yes, no, or a multiple choice. And please don't And it can be very specific and it could even be like, are you sure you didn't make a mistake in question 3? I mean, be polite, but don't just say something in your text like, in question 3 of the midterm, blah, blah. Like, don't make me get off the couch and go find question 3, because that'll just slow us both down and blah, blah, blah. So somehow, even, I don't care if I have to read a really long text. I don't care if you screenshot an image or something like that, but like, I can read, but make it so that what I have to write is super fast and super concrete to you. Like, make it so that if I could just tell you a yes or a no, or if I could just tell you, oh yeah, turn that into a 3, or yes, you're reading like, make it so that I can do that. And then I will respond. And a number of you have been doing that already, like no names here, but anybody who has used my cell phone thus far has used it in a way that really does work for me, and I hope works for that person. Okay, so even once the exam gets posted, you'll be allowed to ask me questions if you want. I mean, and if I don't want to answer it, I'll tell you I can't answer that. But okay, but the other thing is, please do, if you're not sure about something, like, watch the video first before you text me. Like really, like this, if you've never seen one of these videos on YouTube, this is a good time to start. And don't forget to like and subscribe. No, I mean, but seriously, make sure I didn't already answer your question in the video first. I'll still try to be polite and I know people, you know what I'm saying, okay? So what you're gonna have here, what you have in your Google Classroom now is a written document of scrawled out, like fast, scrawled out answers. I want to remind you again, I'm gonna say this again now, you'll see it on the video again now. Well, let's turn to it. Hold on a second. Like what we've already talked about is that in the part 1 of the exam, not only have I written out these answers for you, these solutions, and I think I've walked through them. I think I walked through a lot of part 1, but the way I'm writing them out here, hopefully somewhat neatly, clearly, thoroughly, that's the kind of thing I'm looking for from you. The rest of the exam, I scrawled out stuff so you could see what's correct and incorrect, but you're gonna have to do better than that on your exam. I wanna say that again. Like, don't just copy me verbatim at all, but certainly everything after part 1, you're gonna have to like back up and make sense out of what I'm trying to tell you. You might have to watch the video a couple of times or blah, blah, blah. So please remember that parts 2 on in the exam are like answers and thoughts and my help, but they are not full, appropriately presented solutions. You have to present them better. You have to show that you get, okay? So that's number 1. Number 2, as we go through this, and I'm gonna go quick, I'm gonna tell you explicitly parts that will not be on your exam, and stuff like that, so you follow me. So, okay. So in fact, I'm gonna start because now, okay, so this practice exam is kind of a monster. Even to me, it's long. There's a lot of details to it. It's pretty intense. And there's even some errors in it I've now found out. So it may be a stressful document for you to navigate, or it may have been so far. What I'm here to, and I know you didn't get all the answers until like right today, and today's our second to last day to talk about it. And also, don't forget, I keep forgetting, still on Monday, we still have class. And still, the exam's not due till Wednesday. So even on Monday, you can still come in and ask questions and stuff. So I really actually shouldn't be freaking out quite so much right now. But in my mind, I want to be done walking you through this thing today. And then by Monday, you're at the point of like having detailed questions and things like that. I'll still answer them Monday. But the one warning, or the good news I want to tell everybody now, and again, I can't put this into words except to say it. Sorry, I'm going to change the view here. And please stop me if I'm already not being clear or something. But one thing I'm going to tell you, because this exam is long, and it's in parts, in places, it's more complicated than I wish it were, honestly. And even in some places, it's like, because 2 authors wrote it, there's like a little bit of muchness to this exam, and I'm aware of that. So I'm going to tell you right now explicitly, I'm going to tell you right now explicitly that, except where I note otherwise, your exam will literally be identical to this. I mean, I'm going to take out certain parts, but I mean, for the most part, I'm not going to change. You can expect that whatever you see here literally is what I will post Thursday. So like, really understand this. Don't worry about, well, I kind of get this, but like, if it's too different from this, I don't know what to do. It won't be, especially because, okay, so like, I'll just stop talking. I'll be more clear as I go. But if you understand this, you will not be surprised when you see yours. And parts of this will be removed, and I will tell you that as we get there. But okay, so part one will be just like this part one. But since we went over it thoroughly, I think, and since it's written out thoroughly, the worst thing I might do in any of the part one stuff, I might change a number here or there. So be careful with that. I probably will change like a number. So make sure you can really do these things no matter what the numbers are. But I won't change the concepts. I won't change anything but maybe for some numbers. In part one, that's in part one. I might change numbers. That's as bad as it'll get. Otherwise, it'll look identical. That's part one. Then we get to part, yeah, that includes problem one, problem two, problem three. So the chopper, the plushie, all those, just know them well. They will be just like that on your exam. Oh yeah, okay, I hope I can say this quickly. Notice in the chopper problem, I'll try to say this as quickly as possible. You know, you've got this chopper going up, it drops a package. The chopper, again, I'm looking at the page. Yeah, I'm looking at part one, problem three, problem two, the chopper. The chopper's going up, the package is underneath, then at some point the package drops. Just please, it drops out of the chopper. So relative to the chopper, the initial velocity of the package is 0. It just like drops out. But what I said last time, but please realize this exam is a lot about Galileo's principle of relativity. So if the package is doing nothing relative to the chopper, but the chopper was at that moment going up at 20 meters per second relative to the ground, that means that the moment the package came out of the chopper, it was going 20 meters per second up relative to the ground, i.e., for all intents and purposes, even though it's a hard idea to assimilate, maybe you might want to think about it, but I'm saying that package did not immediately start falling down. It first was going up for 2 seconds. Then it came down for 2 seconds. So it ended up going nowhere. I guess I did say that already, but that's the kind of thing you really need to understand in your mind before you write it down. And you may want to make it as clear as possible that you get that in your exam. But anyway, so the answer to that was 120. I know I'm going fast again, but I think I said that last time. Also, last class is also, of course, going to be posted. It technically is already on YouTube. I just haven't put it in your classroom yet. But certainly this class and the last class are available for, and you don't ever have to like the videos or anything like that. But I guess if you actually do subscribe, it might help my life somehow. I don't know. I don't even know how that works. But all right. Similar thing in number 3 of part 1. Just follow. I don't think there's anything worth saying about it right now. Just look at my solutions. They're correct. If you have questions, you can text me, whatever. I think the main trick of problem 3, part 1 is it's trying to force you to understand the difference between average velocity and instantaneous velocity. Like that puck traveled 144 meters in 12 seconds. So its average velocity is 144 times divided by 12. That means on average, it's going 12 meters per second, but it was slowing down the whole time. So it doesn't go 12 meters per second every moment. And it certainly doesn't go 12 at the beginning. It goes 12 in the middle. Its average is 12. So then from math, what I end up figuring out is that means at the beginning, it was going 24 because at the end, it was going 0. It slowed down to 0. So if 12 is in the middle and 0 is at the end, then its first velocity must have been 24. Like I'm figuring out with equations on this sheet that you're looking at right now, but it's also just, hopefully if you just think about it, it makes sense. If on average it was going 12, then, and if it was always slowing down to 0, then it must have begun at a top speed of 24. But okay, so just as long as you see that, that's sort of the issue of that problem is don't confuse instantaneous velocity with average velocity. Okay, wait, I'm just changing view here. I'm gonna keep it. Again, stop me, please, if I'm being if I'm being too fast or too frantic or whatever. So that's all part 1. Again, part 1 will be exactly as is, except I might change numbers, but I won't change them enough to change what's going on. Okay, right. So from here on in, I'm just scrolling out. Okay. The riverboat, this next problem, part 2, which is really about Galileo's principle of relativity. Like, I could talk about this problem all day if I'm not careful. Some of you might have to think about it all day to really understand it, but not because it's complicated, but because in a way it's so simple. Okay, this problem's not easy, but it is simple. What do I mean by that? I mean, in this problem, part 2 of the exam, it's really trying to force you to understand this idea about relative velocities, how all velocities are relations. Like this goes back to train of thought and all that stuff at the beginning, which all seemed abstract, but we're trying to show you now how it really applies to problem solving. So what I'm saying in part 2 is it's simple, in the sense that there's no acceleration involved at all. In any of the things of part 2 in that river problem, there's nothing ever speeds up. So everything is constant velocity. By everything, I mean the river is constant velocity, the boat is constant velocity, the bottle is constant velocity. It turns out to be 3 different velocities, but they're all constant. So equation-wise, the only equation to use in this problem at all is average velocity equals displacement over time. Or you could say distance equals rate times time, if that's how you think of that. That's the only equation I'm using here. But the issue is that there's 3 different objects. And the issue is that, remember, velocity is relative. It's a relationship between, there's no such thing as what's my velocity. There's what's my velocity relative to the Earth, or what's my velocity relative to the sun. 2 different things, right? And if you recall, the velocity of me relative to me is always 0. The velocity of me relative to the sun is always the exact opposite of whatever the velocity of the sun is relative to me. Okay, that's actually GPR form number 4, if you look in your notes or whatever. That's the concept that's happening. And also remember, every frame of reference is equally legitimate. Like the laws of physics are the same from my perspective as they are from your perspective, as even if we have 2 different perspectives, even if we're moving at 2 different velocities. Okay, so this problem is very conceptual that way. The math is not the hard part. Well, especially if you do it conceptually correctly, the hard part is knowing how to set up the math correctly. So I'm going to say this like once, you really might, but I've had years where we've had like 2 days of debate over this. Like you really might want to argue amongst yourselves or even look it up on the internet, what I'm about to say, but really, but here, I'm about to say something, but when you hand in your solution to this problem, and it definitely is on your exam, and here too, here I'll tell you, I definitely won't even change the numbers. It will literally be identical to this. Okay, so I'm telling you right now, the answer to this is 1.5 miles per hour. But if you just write that, or you write it quickly or something, or you just write one equation, write 1.5, there's no way you're getting full credit for this. The thing that you need to do is really show that you get how to get the 1.5. So I'm going to tell you right now, and it's not hard to say, it's not even hard to write, but it is hard to believe maybe and understand. So please take me serious on this. Here's the deal with this problem. I'm just watching the time while I say this. Okay. And I didn't even include it. Remember also the way I wrote, let me put it this way. The answer is 1.5, but if I were grading my own exam right now and I were grading this thing that's on the sheet, what I wrote on the sheet is there to help you, but I would not give myself full credit for that explanation. Like there's no diagram there's nothing labeled. I don't even know what S or W stands for. So you got to slow that down and show me, but here's what I'm doing. Here's what I'm saying. The issue of the problem is there's a river flowing, right? And it's like flowing down the page. It's just, that's down the page is the direction of the current. The river's flowing down. Okay. And there's this boat, as you see from the picture, there's this boat going up the river, right? So they're like paddling. And the minute the boat crosses a bridge, and the bridge is just like where we start the experiment. It's just like an arbitrary place. The minute the boat crosses the bridge, it drops a bottle out of the boat, right? Again, I'm just stating the problem here. So a bottle falls out of the boat, falls into the water. What does that mean? It means from now, it's kind of like something like a package falling out of a helicopter. It means from now on, the bottle's not affected by the boat. It's just going to do whatever the water's doing. Like it falls into the water and just travels with the water at the constant velocity of the water. It's like, again, this is not gravity. When we say downstream, we don't literally mean down. We mean like south or something, right? So the bottle is now in the water from the moment the problem begins, from the moment the boat crosses the bridge. The bottle's going down with the water. The speed of the bottle relative to the water, in other words, is 0. The speed of the bottle relative to the shore is exactly the same as the speed of the water relative to the shore. In other words, the speed of the bottle is the speed of the current. What is that speed? It's not given. It is the question. The question is, how fast is the water / bottle going relative to the shore? I don't know when I begin the problem. It's what I'm trying to solve. We're trying to solve for the velocity of water relative to shore. What I think I call here, or technically, yeah, no, I'm trying to find the velocity of the water relative to shore, like VWS. Now, it turns out, you'll see what I end up solving for the speed of the shore relative to the water, and you'll see why. But then I say, oh, they must be one and the same speed, just in opposite directions. So whatever number I get is the answer. Okay, so we're looking for, what we're looking for is if you stood on the shore, how fast would you see the water going past you? And I'm telling you, what we've been saying in class is, that's the same thing as asking, if you were standing in the water watching the shore go back that way, what speed would you see it doing? Like, from the water's perspective, the shore is going north. From the shore's perspective, the water's going south, but it's got to be at the same number. Okay, that number, whatever it is what I'm solving for. I eventually got an answer of 1.5, but where the heck did I get it? Here's where. Now, because there's two other facts that the problem tells me that come into play. The problem tells me that the bottle is dropped out of the boat right at the moment that the boat crosses the bridge. What happens from then on in is, the boat keeps going up past the bridge. The boat keeps going at some speed relative to the water. I don't know what it is, but it's some speed, right? Like the boat's going like this, right? So it's going fast enough, in effect, to like match the current, and yet even faster, so it can go up, right? That's what the boat's doing at some constant speed. That I don't know. But I do know that, or it's given in the problem that I think 20 minutes later, as the boat's doing this, going up, 20 minutes later, all of a sudden the people in the boat are like, oh no, we dropped our bottle and like we want to get more drunk or whatever. So they instantaneously turn around. You know, it's kind of like our early problems in the class. You don't have to worry that it took them any time to turn. They turn around super fast. And now they start coming down to chase their bottle, right? So now they're paddling. Now, in your mind, you might think, oh, it's easier to paddle now because they're going down. Yeah, you're probably right. It is probably easier to paddle now that they're going down, or could be easier if in fact, they could just not paddle at all, and they would just like now start flowing with the river. But if they do that, if they don't paddle at all, sure, they'll be going down now, but they're never going to catch their bottle. I hope you understand, right? If they just turn around the boat and let the river carry them down, well, that's exactly what the river's doing to the bottle, and the bottle's all the way down there. So they would never catch the bottle just sitting there. So they paddle, right? They paddle, and what the problem tells you, and this is a little bit tricky, it says that whatever speed they go down relative to the water is the very same constant speed that they went up relative to the water. Now, let me make that as clear as I can. Like, this again is about frames of reference and perspective and relativity. This is about the concept of physics, not the computations of physics. So what I'm saying, they're now paddling on their way down. If you're thinking in your mind something like, oh, well, I guess they must be going super, like if they're paddling like the same strength as they always were before, they were fighting the current, but now they're with the current. So they must be cooking down. Now they must be really going fat. Like in other words, what I think, maybe I hope you're thinking unconsciously is, if someone were watching from the shore right now, they would have seen a boat sort of struggling up, a boat with like a speedometer that says like 5 miles per hour relative to water, like they're passing water. But now they're seeing a boat that's still going 5 miles per hour relative, or whatever number, relative to the water. But since the water's carrying them, if you watched from the shore, you would be very right if you're thinking about what you would see from the shore, you're right to believe that they were kind of chugging up and now they're zooming down. Like they're going at two different speeds according to the shore. That is true. But it's because you're told they're going at the same speed relative to the water. Remember, all frames of reference are equally legitimate. They're all correct. They're all going to get different numbers, but they're all correct, the laws of physics. So this is where physics really, and I hope you're following. And again, if you're not following, but at any point today, by the way, if there's something I'm saying, if you're really hanging on and listening to me, but something goes too fast or you don't understand something, even if I put it in the chat, because even if I can't answer it right now or something, at least I'll see in the chat where you're confused and I'll bear it in mind and okay. So, but anyway, I'm saying right now, relative to the shore, the boat goes up slow and back down fast. Relative to the water, we're told explicitly, like if I were a lily pad in the water, or better yet, if I'm a bottle in the water watching this boat, well, then the boat's going up at some speed and then it's coming down at the same speed relative to the water. I still don't know what that speed is, but it's the same one, like both ways. Okay. And the last fact we're given is after all is said and done, after the boat goes, so boat and the boat crosses the bridge, it drops the bottle. So the bottle's going down like this. The boat keeps going above the bridge. If it suddenly turns around and starts chasing that bottle, now it's chasing it. It's going fast relative to the water. And so it is going to catch up to the bottle. It will. And where does it catch up to the bottle? We're told it catches up to the bottle a mile below the bridge. Okay. If you're watching from the shore, you'd be right to think that the boat does something like this. Like it goes up some amount for 20 minutes, and then it comes down like a much longer amount. If you picture something like this, then you're understanding the problem correctly. And if you think, well, this is complicated. Now, how the heck can I figure this out? Like, I don't even know how to put these facts together. If you think it's complicated and hard to put the facts together, you're absolutely correct if you continue to watch the problem from the perspective of the shore. From the shore, things are complicated. It's slow, and then it's fast, and it's short, and then it's long. It is complicated to watch from the shore. But this is the thing of relativity. If you observe this problem or analyze this problem from the equally valid frame of reference of the water, in other words, if you just pretend in your mind you're like some water molecule, or better yet, pretend you're the bottle, right? Because it's just floating along in the water. Then from the bottle's perspective, the boat goes up at some speed, right? At some speed for 20 minutes. It goes up at some speed for 20 minutes. So again, I'm being the bottle right now. I'm in the bottle's frame of reference. And this is like, being in a video game or a cartoon or whatever, the camera is on the bottle now. And this is a valid physics thing to do. In fact, it's a crucial physics thing to do. In fact, if you've ever played video games or you ever have any comfort with like if you play Minecraft or something, and sometimes you can watch, I guess they call this first person, third person or something. The fact that you could sometimes look at the Minecraft guy walking around, or other times you can just be the Minecraft guy watching, that is like legitimate physics. In fact, it's the heart of physics, that our ability to do that legitimately. We're going to do that right now. We're watching the problem from a camera that's on the bottle. And if we do that, then think about this. Then we see a boat that goes away for 20 minutes, right? And then turns around and then comes back to us. Like the boat eventually catches up with the bottle, right? And that's what we're told. Where? Like a mile below the bridge. So for a minute, forget the bridge, forget the shore, forget all this complicated crap. If you're the bottle, you just see a boat going away from you for 20 minutes and then coming back to you. You see a boat going away at some speed for 20 minutes and then turning around and then traveling at the exact same speed relative to you and eventually coming back to you, right? Now, you might have done something during that time. Like, in other words, while that's happening, the shore is going up, fine. But don't even think about that for a minute. If you're with me, that the boat went up for 20 minutes at some speed and then traveled at that same speed relative to you and came back to you, then the boat made a round trip relative to the bottle, right? Relative to the bottle, the boat went up and then down. Now, again, maybe the bottle moved during that. But that's just compared to the shore. So if you put a camera on the bottle, you're going to see the shore going down while this is happening, but I don't care. For the moment, I don't care. I just know that if I'm the bottle, I see a boat go up at some speed and then come back down to me traveling at the same speed. So it went a certain speed for 20 minutes and then did that same speed and came back the same distance to me. What is that distance? I don't know, but it's got to be the same because it's a round trip. Boat left me, boat came back to me. So I don't know, maybe I'm saying this, I don't know how I'm saying this, but I'm saying it. That means the boat went up for 20 minutes and then came down for 20 minutes. It must mean, in other words, the boat it doesn't say it in the problem. I'm saying this is analysis now. If we're told that the boat turned around 20 minutes later and then started traveling back to the bottle. And if we're told that it continues to go the same speed relative to the water, then since it's going the same distance back and it's going the same speed, it must take the same time to go back. This is crucial. Again, please play this again in the video or whatever, because the more you think about this, the more you might get confused at first. And that means you're thinking correctly. I am literally saying, I'm not saying the problem told me it was 20 minutes up, 20 minutes down. I'm saying the problem told me it's 20 minutes up and it's same speed down. And I'm telling you that it must be the same distance in this frame of reference. So I'm saying that I know that's where I get this 40 from. Okay, like let's scroll down here. I'm saying I know for a fact that this whole problem took 20 minutes and then another 20 minutes. It took 40 minutes for the boat, necessarily because of all the physics I just said. This whole problem must have taken, this whole round trip of boat must have taken 40 minutes. And now here's the crucial point. And again, this is the kind of thing you would want to put in your words or with your picture or something, show that you get it. But I'm saying what I think I just proved is that the whole problem must take 40 minutes. Now there's one other fact in the problem that I haven't used yet. The fact is that evidently the boat and the bottle reunite a mile below the bridge. What does that mean? It means from this perspective, if the camera is on the bottle, it means if I'm the bottle, I watched a boat go for 40 minutes while also out of my eye watching the shore, right? Watching that bridge, right? I watched a bridge travel away up from me, right? Like I'm traveling down from the bridge. So if I'm the bottle, I watch that bridge go up away from me. And according to the problem, is the minute the boat comes back to me, that bridge evidently is a mile above me, right? I'm a mile below the bridge. The bridge is a mile above me. So what that means is that in 40 minutes, the bridge traveled 1 mile relative to the bottle. The shore moved up 1 mile per 40 minutes relative to the bottle, relative to the water. Therefore, the water was flowing down at 1 mile per 40 minutes, i.e. then reduce the fraction or fix the fraction. In other words, 1 mile per 2/3 of an hour. In other words, 3/2 miles per hour. That's it. It's 1.5 miles per hour because the math couldn't be simpler. The math is 1 mile was elapsed in 40 minutes of time. That's it. But to understand how I could make the only way we can the math is super simple. And if you just write down those two equations on your exam, that's not full credit. That's an algebra test. What I'm saying is we got the math to be that simple by thinking physics, right? Okay, I don't want to overstate it, but I also say, and I'll try to post this, I've had in the past people do class projects. Well, I always have. And I'll post later. I've at least on the YouTube channel somewhere, if you like scroll through somewhere in the weird videos of my YouTube channel, there's at least 2 video simulations of exactly this. That's actually, there's 3 that students made in the past. And then that you can just watch, and at least 2 of them have like 3 different camera angles going at the same time. Like you can watch this problem occur from the bottle's perspective, from the shore's perspective, and the boat's perspective on videos that are on my channel, but I'll post the links later if I remember. Okay, if you're like if you don't like what I'm saying. All of what I'm saying too is, by the way, you don't have to solve the problem from the water's perspective. You don't have to do it my way. You could stand and watch from the shore, and if you do all your equations correctly and carefully, you'll get the exact same answer as me. I'm not saying this is it's true because it's true. You'll get the same answer from any perspective, but it's a heck of a lot of super complicated math that gets really easy to foul up and really hard to follow if you do it any other way. This is an example of the difference between physics and math. We use the physics to make the math as simple as we can, but we're not lying. Okay, so that problem is definitely on your test, and it's definitely going to be exactly identical, and I'm not going to change the numbers. So there's no secret what the answer is, but the better you can show that you understand what I'm saying, that's where all your points are going to come from. And again, talk with each other, blah, blah, find my videos. Also, you can even look this up on the web. The original, this is a classic physics problem that actually used to, famous physics professors used to get right, and a lot of math professors used to get wrong. On purpose. The guy who invented it was a Nobel Prize winning physicist from Russia. His name is George Gamow, G-A-M-O-W. You can look up this problem if you want. Anyway, but so that's the deal with that problem. Okay, and you can also call me and all those things. But that's the deal with that problem. That's part 2, definitely on your exam. Then we go to, I'm just checking the time. And again, I'm sorry, I'm like yelling and stuff. Please, put something in it. And I also, frankly, I can't even see your faces right now because I'm trying to make sure that you can see mine in the video. So I won't even see it if you raise hand. So please put something in the chat if anything I'm saying is something. All right, that's that problem. Then we go to part 3. Now I'm going to warn you about part 3. Part 3, I actually didn't write. It was on the exam last semester, so I'm putting it on here. It's based on a problem I originally wrote, but then Professor Walters made it even hard. To be honest, he was really worried about cheating last semester, so he made it sort of extra complicated. So Chegg couldn't do it, which is sort of fun. But this will be on your exams problem too. But it's a little overcomplicated, and I will tell you right now, I will change the numbers on this problem. I will definitely change the numbers only because the numbers don't really work very well. And I realized that by the time I got to the end. I'll be more clear in a second. I will change the numbers. And to be honest, your version might even be simpler. Like I might even take out one detail just because I understand that this problem is a bit complicated and not perfect. There's no way your version will be harder. The numbers, if the numbers are changed, it's to make them work out better. Let me cut to the chase to the end and tell you what I mean. It turns out there's something wrong with this problem where the question says how high above do the 2 objects meet? And the way all the numbers work out, they actually don't meet above the window. They actually meet below the window. And in fact, they meet way below the window, like below where they were even thrown from. All of that is physically possible, but it does make it confusing. You'll see, I get this enormous negative number as an answer at the end. That's not technically wrong. It's right, but it is confusing and annoying. That will not happen to you on your exam. Again, this is the kind of thing you could only know if you are hearing me right now or if you watch the video. But this problem will be on your exam. But first of all, the numbers will be changed, so there isn't that issue. So I'm going to skip to the end of it for a second just to show you what I'm talking about. I mean, I will tell you how to do it, but I mean, I did write it down. Like if you can follow what I'm doing, and this is actually right where, if you follow what I'm doing, it's like correct and everything I'm doing, like to page 13, page 14. Then I get to page 14. Frankly, this is exactly where the solutions cut off on Monday. And they cut off there because right when I got to this point that t equals 8.27 seconds, that's when I realized, oh, this problem's kind of a mess. Okay, so everything to do to that point is the correct thing to do. Everything I do from there on is still correct, but everything I do from there on shows that the original presentation of the problem is a little bit thick. So like where it says at the end, so they meet 329 meters below the top of the window. I believe that's the correct answer. But first of all, I know the problem said how high above the window do they meet. So I'm not trying to trick you here. I'm just admitting I think there's a flaw in the problem. I will take that flaw out of yours. You don't have to be worrying that I'm gonna trick you like that. Second of all, they meet so far below that it's even below where it started. That again, please, if you're listening to me now, know that I apologize. That is not meant to be a trick. It is overly tricky. I will simplify on the exam. I can't promise this. It's also hard that there's 2 objects and stuff. Now, you know what? I'm going to tell you this. If you're listening right now, here's a benefit. If you're actually paying, I will tell you right now, this problem will appear. But I'll tell you right now what's going to happen. If you're listening, this is the reward for listening. This problem will appear, but there will only be one object. It's either going to be a rock going up or a flower pot coming down. It's not going to be both. Okay. And let's assume it's a rock going up. I'll even say that in your can I say that? I have to think that it's either going to be a rock going up or a flower pot coming down. It is not going to be both. And I am promising. I can't promise which one it'll be, but yours will only be one object. And the question you will be asked, I'm telling you right now, if it's just a flower pot falling down, then what I'm going to ask you is, how high did the flower pot come from, period? Or if it's a rock going up, then I'll ask, how far below was the rock thrown from, period. Okay, that's all so you'll basically have to do half of all of this work. So what I'm going to do right now is try to explain the key part that you definitely will have to do. Okay, so go back to the beginning. Notice, yes, notice right here on page 12, right when I start analyzing it, I start by just analyzing the rock, okay? So imagine you just have a rock in this problem. Like, don't even worry about the flower pot. Imagine that all you're told about this, and this is what would happen in your problem. Like in this version of this problem on the exam, you're told a bunch of things about the rock, but the key, okay. Well, yeah, you're told a bunch of things about the rock, but the first key thing that you're told, the first thing that the key thing that you're told is that the whole window is 2 meters from top to bottom, and that the rock takes a half a second to travel past that window, right? Now remember, whether we're talking about the rock, which happens to be moving up, or we're talking about the flower pot, which happens to be moving down, either way, it's free fall. Either way, because only gravity is involved. Like nothing is touching the rock, nothing is touching the flower pot. So either way, we're talking about free fall. In the case of the flower pot, it's something falling down, therefore speeding up at a rate of 9.8 meters per second squared. If it's the rock, it's moving up, but it's slowing down at a rate of 9.8 meters per second squared. Either way, we have a constant, and which you can round to 10 definitely. Either way, we have an acceleration that is constant and that is pointing down at a rate, always down at a rate of 9.8, either way. And the key point being that it's constant. So either way, it's constant acceleration. So now we look at that rock. We're told that the rock, that it's 2 meters of displacement and it's a half a second of time. So what you should do, and what almost all of you would do or do if I said nothing, what the first instinct you might have is, oh, okay, 2 meters of displacement, quarter second of time, displacement over time equals average velocity. So for that, so many of us, our first thing to do would be, okay, let's get the average velocity first. And that's what you should do. That's what you always should do, because it's something you can always rely on. That's why we began the year with it. Average velocity is defined to be displacement per time, so it's never wrong. It's a definition. So so the first thing you might do correctly is say, and where am I? I'm right. I'm where I am right now talking, sorry, is right over. Yeah, I'm right. I'm just at this step right here. The first step you do, displacement over time, you get 4 meters per second. That lots, and that's what you should do, even if you're really confused by all the details of the problem. Like those are the first 2 facts you see. Take those facts, divide them. You have a fact now. Now, the important next step, this is kind of like all the practice we were doing right in the beginning of the semester, is realize that's the average velocity of the rock past the window. That's the average velocity. The rock is slowing down the whole time it's going. So it's changing its velocity every instant. That is not a constant velocity. Acceleration is constant, but that's not a constant velocity. That's an average velocity. What that means is that the rock is slowing down as it's going, but its middle velocity is 4. That's its mean velocity, but since we're in constant acceleration here, it is fair and smart to believe that's its median velocity as well, right? Constant acceleration means the mean equals the median. So what you can so 4 meters per second is not the instantaneous velocity at every moment. That would be the mistake that a lot of people would make. And it's not the velocity right at the bottom of the window or right at the top. It's the middle velocity. It's the velocity right in the middle of the time of that window. And all this you will do on your exam. So I'm saying once I know that the velocity is going on average at 4 past the window, then I go down to here. Oh, well, then I'm thinking this, like, okay, that's its middle velocity. In effect, its fastest velocity at the bottom of the window must be equally spread around. Forget that point. So now if I want to know exactly how fast is it going, either at the bottom of the window or the top of the window, what do? I think about acceleration now. I realize, excuse me, I realize every second this rock is losing 10 meters per second of velocity, like 9.8 rounded. Every second it's losing 10 meters per second of velocity, continuously all the time. That's the meaning of acceleration here. So So now I'm writing out with equations, I'm rearranging the acceleration to say, oh, if I know the acceleration and I know the time and I know one velocity, which I do, I know the velocity right in the middle of the time, then I can figure out whatever I want, either the beginning velocity or the end velocity. Like I know the V naught, I know the A, I know the T, I'm looking for a V. Like that's what's happening here. And the math gets me, if I'm careful, like acceleration pointing down at -10, velocity pointing up at 4, right? The 4 that I got from up here. So I just did math and got 1.5. But in English, what I'm saying about that 1.5, if you think about it, is I'm saying, look, every second this rock is losing 10 meters per second of velocity. Every second it's losing 10. So in the middle of this window, it had a velocity of 4, but the whole window is 0.5 seconds in duration, right? That means in the middle of a half of a second, it has a velocity of 4. So what I'm looking for is what's its velocity a quarter second later or a quarter second before, right? Because the whole thing is a half second. And right in the middle of it, it has a velocity of 4. So if I want to know how fast it's going a quarter second later, remember it's slowing down 10 meters per second every second. It loses 10 every full second. I don't want to know about a full second later. I want to know about a quarter second later. So a quarter second later, it doesn't lose all 10. It loses a quarter of 10, 2.5. Like that's what the math is saying, but I'm trying to say it makes sense. This thing has a velocity of 4 right now. In a quarter of a second later, it will lose a quarter of 10 of its units. So it had 4, so it loses 2.5. So at the top of the window, it has 1.5 meters per second of velocity. If you're following my logic, you'll understand that by the same reasoning, I could say at the bottom of the window, it's going 5.5. It's like 5.5 meters per second, slower, 4.0 meters per second, slower, 1.5 meters per second. I'm sorry, I just said 5.5. I mean 6.5, right? I mean to be consistent. 6.5, 4, 1.5. It's losing 2.5 every quarter of a second because it's losing 10 every full second, okay? If you follow what I just did, this is actually the heart of the problem. I know there's all these equations that it looks like there and all this complexity. The main thing to see is the piece that I just said, that sure, you can just go right ahead and go, 2 meters, 0.5 seconds, that's 4 meters per second. But you got to understand what that 4 is. That 4 is its average velocity, which means it's instantaneous right in the middle. So it's instantaneous at the top, according to this, is 1.5. Okay, so now here's where I'm going to depart from the thing. Now a whole bunch of stuff happens because like then the flower pot gets involved and stuff. On your test, there will not be a second object. Let's just keep going mentally right now with this. You might have to play the video a couple times, but let's say that the whole question now is, okay, then how high does the rock get before it falls down again? Like that would be the most reasonable question I could ask right now if we were following the rock. If I just asked how high above the, in other words, instead of asking how high above the window will the rock meet the flower pot, forget that. Just assume I'm going to ask how high above the window does the rock reach before it starts falling again? Like what's its peak height above the window? So I'm going to add that paper right now. Hold on. In fact, you know what? I'm going to tell you right now, this will be the question. Okay, literally, this will be the question is, so forget the flower pot, just believe everything I'm saying about the rock, and I don't have to change the numbers or anything. Like the rock does this. If I now ask, how high above the window does the rock ever get? Then how do you solve it? Well, what you're doing now, then, if you follow this so far, is you now have a rock that is sailing past the top of the window at 1.5 meters per second. and I'm asking how much higher does it get? That is literally like me asking, okay, I throw a ball up at 1.5, what's its peak height? Remember, this is what we were drilling and chilling in our heads like weeks ago. So again, if you're listening to me right now, I'm guaranteeing you this will be my question. I'm just going to ask, how high does the rock get? And I'll remind you right now, if I said that the rock was, if we just knew, like outside of this problem, if I just had a rock and I just threw it up at 30, right? Remember what we were doing in our heads. Like I could show you with the equations again, but remember what we were doing. If I threw something up at 30, we used to say, oh, if you throw it up at 30, well, it's losing 10 every second. So it would go up for 3 seconds, right? Like 30 divided by 10 is 3. That's actually is an equation, but I'm just saying it right now. If I threw something up at 30, it would lose 10 every second. So it would take 3 seconds to get to a peak height. And in those 3 seconds, it would travel an average of 30 plus 0 divided by 2, 15, right? Like if, I'm not writing this because this is like a hypothetical, just to remind you, if I threw something up at 30, if someone asked me how high is it going to get, I would say, well, it's going to travel for 3 seconds and it's going to travel at an average velocity of 15 because it's slowing down to 0, right? 30 plus 0 divided by 2 is 15. So I would say, oh, it's traveling at an average rate of 15 for 3 seconds. It would go 45. And that would be my answer. If I throw something up at 30 meters per second, you could check me. It will go up 45 meters before it comes down again. Well, I'm going to do the same logic right here. Like I could do it in my head. You could do it on the, I'm saying here, to go one more page. And again, this is what the problem will be. Forget the flower pot and all that. And anybody who's not attending this class or doesn't pay attention is going to have a lot more stress than you. So tell them we're not, as you see fit. But I'm saying now, if V naught equals 1.5, as we just figured out, and if A equals -10, as it does because this is gravity, and we want to know what is Y, I would say, well, do this really fast. Whoa, sorry. Whoa. I forgot I skimmed those. Sorry. I forgot we're looking for time, right? So we go like this. Okay. Right, so the thing I'm saying right there is, okay, if it's going up at 1.5 meters per second, then it's going to travel for 0.15 seconds, right? That's just like what I did before. That's the time. And the height that it's going to go is going to be the average velocity times that time. So the average velocity will be right, is 0.75 meters per second. From 1.5 to 0, the average is 0.75. So this whole thing goes 0.75 meters per second for 0.15 seconds. And if you do the multiplication, that means 3/4. So 0.0325, I believe. You might want to check my math there. 3/4. No, that's not right. 45 divided by 4, right? So you might want to check the math, but it's about 0.11 meters. That would be the answer. And I'm telling you, that's what again, maybe I don't know if I went too fast or too slow right now, but I am saying, again, that will be the extent of your version of this problem. Forget the flower pot. Your version of this problem will just be the rock. And I'm just going to ask, how high above the pot, the whole window does the rock get? Okay. Oh, okay. Thank you. Thank you so much. Great. And I'm particularly psyched that it was you that did that. Great. Because I know you. Okay. Great. And I do believe you. Okay. Great. Thank you. So that would be your answer. And again, you can bank on this. This is now your exam problem. You have to explain things like, basically the point of this video too, or this class is, please understand that everything I'm saying in words, especially the things that make sense to you, that's what you want to give back to me in your words or your pictures or your equations on the exam. English is not only acceptable, it's encouraged. The more words you can give me, the more you can put it your way, the better. The answer is now that I got confirmation from Antonio, I'm going to say that is the answer to the question that you will get. I will not change any, I don't have to change any of the numbers because I'm just going to remove the flower pot from the whole thing. And the fact that it says that the rock was thrown from below the windowsill, it doesn't even matter to this. Okay, so this is now your exam problem. That is your answer. Your job is to show me that you get why that answer is that answer. I hope everybody's, okay? So that's that problem now. Okay, that's part 2. And again, let me just say, if you've had any stress with that problem, or if you even, by the way, there might be some of you who are sort of trucking along and then you got to the middle of that problem and it got so frustrating, you might have given up on this whole thing, or you might even think, I have no chance on this exam. I can understand that. I frankly got frustrated in this problem. So please also understand, I'm changing this. Like, give yourself another chance. Give the exam another chance. Don't fully give up because of that frustration. I felt that frustration too. You're not crazy. It doesn't mean that you don't know physics, okay? And that's also why we're having this class right now. Also, don't forget, if there's still issues like this on Monday, you can still ask Monday. But anyway, that's the answer now, 0.1125. That's that. Okay, so that takes care of the rot. So forget the flower pot. I don't care about the flower pot anymore. And also well, anyway, whatever. Again, that problem got a little overcomplicated because there were cheating concerns in the past, and I'm not worried about you guys, but that's why it happened. All right, now the next problem, part 3, starts getting into 2 dimensions now, or seeming like 2 dimensions. It starts looking a little bit more like lab 3 and lab 4 and stuff like that. Two big principles. Let me say, first of all, this problem, you can assume this whole problem here, this Wile E. Coyote part 3, it is on your exam. All of it is on your exam. All of this problem is on your exam. Will I change the numbers or not? I might change the numbers because I think this one does not have problems. It is a good problem. You might have to think about it. I might change the numbers, but I will only change, I won't change negatives or positives or anything like that. I won't. So you have to be versatile enough to handle different numbers, but that's as far as it'll go. Let me give you an overall summary of this problem and the next one, or 2 overall tips for the exam. Number 1, it is a long exam, and in some of these things in these problems, you're given a lot of facts right at the beginning. That's a typical physics thing. You're given all of these facts that now do all relate to the whole problem. Psychologically, it's important to know a couple of things. We will almost never on purpose give you facts that aren't somehow useful or necessary. Like, it is true that ultimately you want to use every fact we give you, and every fact is there for a reason. They're not there to throw you off. That's on the one hand. On the other hand, it's very important to realize that you don't use every fact in every part of a problem. It's very important to remember that. Like, sometimes the reading of these paragraphs, even to me, even when I've written them, my mind is like, oh my God, there's so much information here. I can't even, and I can totally respect that. What you have to know is, and I will try to make some of this simpler, but sometimes we have to give you all those facts to make the whole problem work. But don't try to assimilate all the facts all at once. Try to make a diagram incorporating most of the facts, but understand, in a way, what you want to do is sort of skim the thing, make a diagram, and then as you're going through only look for the facts that you need in each question. Don't try to hold it all in your mind at once. Assume that some facts won't even be relevant until you need them. That's tip number 1. Tip number 2, anywhere in this test that 2 dimensions or more are occurring, like anywhere in this test, if there's an up, down, and left, right, or east, west, and north, south, or God forbid the problem after this, even if there's like north, south, east, west, and up and down, which is 3 dimensions, don't be intimidated by that either. The main underlying premise of all of this is the laws of physics are the same in all reference frames. A reference frame technically is a coordinate system, and a coordinate system can be as simple as one axis. In other words, even if you see things happening in 2 dimensions, like this problem we're about to talk about here with the Wile E. Coyote, it's very much like lab 3 and particularly lab 4, where what we're trying to teach you is well, in fact, you may even write this down. I'm going to write this very quickly. Key principle. key lesson in the background of all the rest of the problems here, or of lab 3 or lab 4, is two-dimensional physics really is just two one-dimensional physics problems. Anything happening in a plane is really something happening in a line while something else entirely unrelated and independent happens in a different line at the same time. A two-dimensional problem is really two one-dimensional problems occurring independently yet simultaneously. That is the key hook for all the rest of this exam, okay? And really that's what you're supposed to be getting out of lab 4. So, and I know I'm watching the clock, so again, I'm gonna just try to only say things that aren't obviously written here. So like with this coyote problem, which again, it will appear as is. I mean, it is good. There's no problems with the coyote problem that I know of. There's a cliff. There's like a, the coyote's on the cliff. He's about to drop a weight. There's a coyote going along. I mean, there's a roadrunner going along, right? And at a certain key moment, when the roadrunner happens to be 40 meters away from the cliff, right? At that key moment, the roadrunner has a certain velocity and a certain acceleration, and the weight drops, right? So the weight is falling down and the roadrunner is coming in, and eventually they meet, okay? So technically it's a two-dimensional problem, but really what it is this is happening while this is happening, and we understand the physics of this and the physics of this, and they don't affect each other, but it's just that they all happen at the same time. Like this problem is over when the weight is at the same place at the same time as the roadrunner, okay? And that's what we're ultimately solving for. How high did this weight come from? So first of all, the method of the whole thing is really, since we know, it's so hard for me to, I get so confused with the mirror imaging thing, but so we're told all these facts about the roadrunner, that the roadrunner is 40 meters away from the cliff and it has a certain acceleration, a certain velocity, and it's going, and we know it's going to get hit by the weight when it's right under the cliff, right? So, and we're ultimately asked, how high must that cliff have been? So the way to solve the problem is say, oh, wait a minute, there's this roadrunner, it's got a certain velocity, a certain acceleration, and it's got to travel a certain distance. So let's solve for the amount of time it takes the roadrunner to do that distance. Like if we didn't know anything about the cliff, if we just knew there was this roadrunner going at 25 meters per second at an acceleration of -5 meters per second squared, and we knew it had to travel 40 meters, we could just do physics. We could do x equals 1/2 at squared plus b naught t and just solve for t. And we would know precisely the time that it would take the roadrunner to get to that point. And so, and that's what we're going to do. We're going to independently solve for the amount of time it takes the roadrunner to get to the cliff. And we're ignoring the weight. The physics is the physics, regardless of whether there's a coyote or not. So we're going to solve for the amount of time it must take the roadrunner to get to that cliff. And then we're going to say, oh, okay, well, the weight like started falling at the exact same moment that the roadrunner was running. So whatever, so we're just now going to say, all right, imagine we have some weight that was falling in gravity and, at a 9.8 at an acceleration rate of 10. Just imagine we had some weight falling down for a certain amount of time, the time that we just solved for. How far would it fall in that time? Whatever that farness is, that's the height of the cliff. Okay, so that's the method. In other words, secretly what I'm kind of saying is everything in this test, everything in this exam is basically either just velocity equals displacement over time, but understand the relative nature of velocities. Like, so half of this test is about Galileo's principle, and the other half is about what happens when you throw acceleration in. And when you throw acceleration in, you get this 1/2 at squared business. Really, there's only those two equations permeating the entire test. The 1/2 at squared equation is everywhere, and v equals x over t is everywhere. That's it. But the physics is to understand that 1/2 at squared applies to this dude, and it independently applies to this dude. This dude is free falling, so it's going to have an acceleration rate of down 10, of like -10, if you want to say. And this thing is not free falling. It has its own acceleration that we're given in the problem. That's 5. Okay, so first and foremost, the whole method is we're going to solve for the time here. We're going to use that time and plug into the business there, and we'll be done. The one final catch, though, and the reason, okay, so again, I don't know if that went, but please replay that if whatever. We're going to, yeah. and it's like the third time it's happened in this exam where there seems to be a lot of complexity, two objects, two axes, like all this. Oh my God, did we ever learn any of this? But we're just saying, break it down, break it down, break it down, you'll break it down. We're just saying this is a 1/2 AT squared situation. This is a 1/2 AT squared situation. Both the T's must be the same, so solve. Now, the reason there's a bunch of other parts to this or a bunch of other things you're asked is, let's look at that coyote. Let's look at that roadrunner. We're given an initial velocity of 25 meters per second, fine. Okay, it's moving forward at 25. But we're given an acceleration in the opposite direction, like we're told it's traveling to the east, but it's got an acceleration pointing to the west. That's just like something that's going up, but has a constant acceleration pointing down. What it means is that this thing is going to slow down, slow down, slow down till zero, right? In fact, you could do the numbers in your head. It's starting off at 25. It's losing 5 every second. So it's going to go 25, 20, 15, 10, 5, 0. And then it says it's constant acceleration. It says it has an acceleration that maintains forever. So if it truly did, if it just kept going at that acceleration, it would be like something that you throw up into the air, like, and it would slow down, slow down, slow down until it got to 0. But then it would keep on losing velocity. So it would go into the negatives. It would come back down. That's what this coyote, that's what this roadrunner is evidently going to do. If we are told that its acceleration is constant forever, right? We're not told that its direction is constant. We're told its acceleration is constant. Just like if you throw something up in a constant acceleration gravity field, it eventually comes down. This roadrunner is eventually going to start coming back because it's going to hit 0 and then go into the negatives of velocity. How do I know? Just because I'm told the acceleration is constant. That's what that means. So this thing is going to be slowing down, slowing down. When I solve for the time, the math gives me 2 answers for the time. And again, I solve for the time and I get here 2 or 8. Why? Mathematically, because it's a quadratic. There's 2 roots, and I didn't do, I happened to factor it, whatever, and I got 2 and 8. That's what the math said. But physically, that makes sense because this thing is slowing down, and then going to come back. So what it's saying is either it's going to hit either 2 seconds. It's saying it's going to reach the cliff in 2 seconds, and the rock could hit it right then. But then it's going to keep going for another 2 seconds, and then it's going to come back. Or I'm saying the numbers wrong, but it's going to go until it runs out entirely. Well, yeah. Remember, the original thing was 25 meters per second. So it's going to slow down for 5 seconds and then come back for another 5 seconds. So 2 seconds in, if you think about it, is like equivalent to 8 seconds out. It's either I get 2 answers to the time, but because the math and the physics correspond. The math doesn't know, it was never told whether I need this thing to be hit on its way out or on its way in. So it could be hit either way. So it's either going to be hit at 2 seconds or at 8. So then I plug in to the other box. So I'm now plugging in. I'm looking now at the weight. If it's a weight free falling from rest for 2 seconds, then it fell 20 meters. If it's a weight free falling for 8 seconds, then it fell 320 meters. Either it's not going to hit both, but if I put a cliff at either of those heights, either way, this will work, and I'll get the roadrunner. I'll either get him on the way out or get him on the way in. So I get 2 answers to the key question of question D. But then just to make sure really that we both understand what we're saying or why that is, like it's not just math, it's physics. Then the question says this thing, well, what if then the roadrunner did do what you probably would figure that he would do? What if the roadrunner, what if there's a new rule that says once he stops, he's always stopped and never comes back? Then how does that affect? Well, then yes, then the cliff has to be 20 meters. Okay. So that's it for that problem. Okay, we're actually on. All right. The Yaverbaum is very, very similar. If anything I don't get to say right now, it is written here and stuff like that. I mean, I will. We've got like 4 minutes. I will talk about the Yaverbaum. It's very similar. It's very similar. The physics is not hard. What I do know is that opening paragraph with all the facts, there's a lot of facts in that opening paragraph that get very confusing. And there's a lot about the Tropic of Cancer and all this. I will try to water down that paragraph and make it more straightforward in your test. I'm going to try. It is a lot to read. And it turns out if you just be calm and use one piece of information at a time, you never have to use all that information at once. But I will try to simplify that. The key thing to know about the Yaverbaum problem is that it really is lab 4 incarnate. If you understood lab 4, then you'll understand this. Don't get bogged down or overly concerned with the tropic business. Do understand one thing. If you look at my diagram, like just, you got to understand one thing. North is not the same thing as up. So north can be to the side on a page. North is not the same thing as up, just right. And a bomb falling down is not necessarily falling south. This plane is traveling from north to south and it's dropping bombs down. That can be hard to draw or to picture and stuff, but just remember that. The key thing of this problem, right, I'm going to finish by talking about this problem, but also in case we run out of time, the very last problem on the whole test, if you look at my solutions, you'll see, I am expecting you to do the first couple of parts. I'm expecting you to understand Galileo's principle for the couple of parts, but at a certain point in that problem, right when it gets into, so I'm skipping around now, I'm sorry, but I'm telling you right now, I'm promising you, your last problem on this test, if I put it in part 4, sorry, the very last problem, the thing of, yeah, the riverbank, the water, and the boat. It's kind of a revisitation of part 2, but now it's blown up in 2 dimensions. I just want to tell you right. I want to tell you right now that the problem is long and stuff. But the minute you get to part D, the last thing I might ask you to do is do this picture that I drew in part D. But from then on, anything in the problem is not on your exam. Like from then on, your exam is over. Okay. Again, if you're hearing me right now, hopefully it's clear. Everything from D on in that very last part, you do not have to worry about. Don't worry about. It's not on your exam. Okay. Your exam ends at worst at D, what should be called D1, but for some reason is called D3. That diagram is the last thing you have to do. And I think you'll be able to understand all my answers to that point if you go back to part 2. It's the same business of relativity. So with the 2 minutes we have left, I just want to sum up the Yaverbaum business. I'm just going to sum it up. Like the computations are there, but here's the deal. You've got a plane going along and it drops a bomb. You got a Yaver going along and it drops a bomb, right? And the sort of heart of the problem is at first we're asked, like if you drop this bomb, where does it land on the ground? First thing I want you to understand is it's not going to land directly below the plane. You got to understand that. This is relativity. Again, this is lab 4. If a plane is going along and drops a bomb, then, or this is also like part 1 of the exam. If the bomb comes out of the plane at a velocity of 0 relative to the plane, that means it comes out of the plane with the same velocity as the plane. That means from the moment the bomb comes out of the plane, it's still going forward at the same rate as the plane. And the plane's rate is tacitly given to you because it's like a 200-meter long plane or a 20-meter long plane that takes a half a second to pass a certain point. That's just like lab 4. You had a marble that goes through a photo gate. You know, the marble is so wide, it takes so much time to go through the photo gate. So the plane is going 200 meters per second. A bomb comes out of it. The bomb is now falling. So in the vertical axis, yes, it has a downward acceleration of 9.8, but it's still going forward while it falls because it never has any, because it was from the beginning, and gravity does not act horizontally, it only acts vertically. So just like in lab 4, it's as though you just threw something off a table. It's falling down, but it's also going forward. So any individual one bomb is going to go like this and land on the ground ahead of where it was dropped. How do you figure out how far ahead? You get the time that it takes to go to the ground, just like you did in lab 4 or with the 1/2 AT squared equation. And then you say, aha, we've got a bomb going forward at 200 meters per second. It's doing that for 14.1 seconds because I figured that out from free fall. So it goes forward 200 meters per second times 14.1 seconds. That's how you figure out how far ahead the bomb is. And each next successive bomb will do the same thing, and this is the last thing I'm going to say, and actually this covers everything. And again, we can still talk Monday. And again, I'm not trying to freak anybody out, but this is the end of the exam right here, or what you're responsible for. It then says, but what if it keeps doing that? Like, what if it keeps dropping bombs one after another? Each bomb, if you took a video of each bomb, you'd see each bomb go like that. But if you stood back and just took a picture at any given moment after the plane had dropped a bunch of bombs, like it's dropped one, it keeps going, it drops another, it keeps going. If you stood back and look at it, what you would see is exactly what's on the cover of this exam. You wouldn't see a bunch of bombs lined up like this, which is what everybody always thinks. And you wouldn't see a bunch of bombs dragging behind, which is what everybody always thinks. Each one of those bombs is traveling forward while it travels down. all at the same rate. So all the bombs are literally, and this is crazy, but like you see on the front cover of the exam, there's a photograph from like World War II. Bombs will just stay in formation in a vertical line below the plane. They're just going to travel in a vertical formation because each one of them is traveling forward at the same rate. They're all going to stay with the plane. So a video of an individual bomb would be a curve, but a snapshot, a frame of all the bombs would be a straight line. Like you might have to, and put one other way, that's why all the nonsense, like the plane, right, it says in the problem that the plane, right when it drops its first bomb, like some elevator thing falls at the same time, but like, so the elevator just falls straight while this bomb is going like that. They both must land at the same time, like just like lab 4, whether you throw something forward or you drop it, vertically, they're both in free fall. So vertically, they'll take the same amount of time to fall. Horizontally, one will fall ahead of the other. That's what's happening here. If you get that concept, that's the point of the whole problem. Each bomb will fall in the curve, but all the bombs will stay with the plane horizontally the whole time. And that's all that needs to be understood to solve the whole problem. That's the whole exam. Again, your exam will cut off in the middle of the last problem. Also, I might make some other shortenings or something somewhere, I can't promise. But I probably won't change any numbers there either because it's complicated. Again, your job is not just to know the right answers, it's to show why they make sense. You've been very patient. You can text me with questions. Oh, so I'm going to post the thing by 8 p.m. It says no later than 8 p.m. Friday. Probably if I'm active, or I might post it a day early tomorrow. I hope it doesn't freak anybody out. If you can't work on it, you can't. But I may not. But no later than 8 p.m. Friday is what it says in the Google Classroom. So that's my deal. No later than. That's it. And it's due next Wednesday. Remember. Okay. I have another class coming in, but are we? If that's sort of okay. Sorry. Are we? Can I just get like a? Did that make any? I hope people could even hear. Sorry, I can't even see. Or can I just get like a? Are we good? Basically. Okay, thank you. Oh, and thank you in particular. That makes me feel good. Okay, because I know you. Okay, good. I'm going to assume that that speaks for every. Actually, many of you. Oh, I just saw the chat. Well, thank you. Great. Great. You're the best. You're the best. We're all going to rock this. I will see. Have a great weekend. I will see you soon. Goodbye. Bye. Thank you. And I will post this too.